Hidden among ordinary river stones are materials so unusual that geologists once questioned where they came from. Some researchers believe the answer may be connected to one of the strangest gemstone materials ever discovered: black diamonds, or more precisely, Carbonado. The surprising part is not how rare they are, it is how easily the clues that lead toward them can be overlooked. Because the search rarely begins with a diamond, it begins with a rock. A rock that most people would never pick up. At first glance, there is nothing impressive about it. No sparkle, no crystal faces, no obvious indication of value, just a dark, weathered stone resting among hundreds of others. And yet, experienced prospectors often pay attention to rocks exactly like this, not because they expect treasure, because they recognize evidence. The first clue is not its color, it is its location. Notice where the stone was found, not randomly scattered across the riverbed, but concentrated among other dense materials near the inside bend of the stream. That observation matters because rivers are natural sorting systems. Flowing water separates material according to size, shape, and density. Lighter particles continue downstream. Heavier materials settle when water velocity decreases. Over years, decades, and sometimes centuries, this process creates concentrated zones that attract the attention of prospectors. Gold prospectors understand this principle well, but gold is only one of many heavy materials that rivers can concentrate. Magnetite, ilmenite, garnet, certain resistant gemstones, and occasionally much rarer materials. The challenge is learning how to distinguish meaningful clues from ordinary gravel. Most people see black sand and move on. A geologist sees a record of transport, erosion, and mineral concentration. Every grain has a source, every concentration has a reason, and understanding those reasons is often more important than the material itself. Because geological evidence points toward where further investigation should begin. Now compare these stones. At first glance they appear similar, but look more carefully. Some are smooth, some are rough. Some contain visible mineral grains. Others appear unusually dense and compact. This is where observation becomes important. Experienced field geologists rarely jump to conclusions. Instead, they ask questions. What minerals are present? How resistant is the material to weathering? Does it occur elsewhere in the stream? Is it associated with specific geological environments upstream? Every answer creates another question, and every question helps narrow the possibilities. Experienced prospectors understand something beginners often miss. The stone in your hand may not have formed where you found it. In fact, many river stones have traveled significant distances. Flood events move material downstream. Seasonal water flow redistributes gravel. Over time, rivers become conveyors of geological information. That is why prospectors spend so much time studying landscapes. A single stone can sometimes reveal clues about bedrock exposures located miles away. Observe what happens when weathered surfaces are removed. The interior often tells a different story. Mineral textures become clearer, grain boundaries become visible, hidden structures begin to appear. Professional geologists frequently compare weathered surfaces with fresh exposures because weathering can conceal critical evidence. A rock that appears unremarkable on the outside may reveal important geological information once examined more closely. This is also where many beginners make mistakes. They search for obvious beauty, bright colors, large crystals, spectacular specimens. Experienced prospectors often do the opposite. They focus on geological context, because valuable discoveries frequently begin with subtle indicators rather than dramatic appearances. An unusual density, an unexpected mineral association, a distinctive weathering pattern, a concentration of heavy minerals. Small clues, but clues that matter. The next step is not guessing, it is investigation. A prospector would examine additional gravel bars, compare material from multiple locations, search for repeating patterns, study nearby bedrock exposures, and gradually work backward toward the source. This process is slow, methodical, evidence-driven, and it is exactly how many important geological discoveries begin. Now something unusual becomes apparent. Although similar in size, one stone appears noticeably heavier than the others. Its surface is darker, its texture is different, and unlike the surrounding material, it contains countless tiny pits and irregular cavities. At first glance, that may not seem significant, but to an experienced geologist, it immediately raises questions. Questions about origin, questions about transport, questions about whether this stone belongs to the same geological story as everything around it, or whether it represents something entirely different. The most intriguing part is that similar textures have occasionally been reported in association with some of the rarest carbon-rich geological materials ever studied. That does not mean this stone is a black diamond. Far from it. Evidence always comes first, conclusions come later. But it does mean the stone deserves further investigation. And what makes this discovery interesting is not simply the possibility of what it might be. It is the geological story it may represent. A story hidden somewhere upstream. A story written in bedrock, erosion, and time. And a story that may eventually lead us toward one of the most unusual forms of diamond ever discovered. To understand whether that possibility is real, we first need to find where this stone came from. Carbonado remains one of the most unusual diamond materials ever discovered. Unlike conventional diamonds, its origin is still debated. Some researchers have linked it to deep earth processes. Others have proposed far more unusual explanations. But regardless of where Carbonado ultimately came from, one fact remains unchanged. If the dark stones found in this river are connected to that story in any way, the answer will not be found downstream. It will be found at the source. The question is simple: where did this stone come from? For a prospector, that question matters more than what the stone might be, because geology is built on evidence, and evidence begins with location. The first step is not to search for more unusual stones, it is to search for a pattern. One stone could be an accident, two stones could be coincidence, but when the same material begins appearing repeatedly, geology starts replacing guesswork. As the survey continues upstream, similar dark fragments begin appearing again. Not everywhere, only in certain sections of the river. That observation immediately narrows the investigation. Whatever produced these stones is unlikely to be spread evenly across the landscape. Instead, it may originate from a specific geological environment farther upstream. This is why experienced prospectors study entire drainage systems. Every tributary contributes material. Every slope contributes sediment. Every outcrop contributes evidence. The river is not simply transporting rock, it is transporting information. And by reading that information carefully, geologists can often trace loose material back toward its source. Look closely at how the dark stones become more common above this junction. That may not seem significant, but small changes in distribution often reveal important clues. Prospectors pay attention to where material appears, where it disappears, and where concentrations suddenly increase, because those transitions frequently point toward the source area. Now, another clue appears. The dark fragments occur alongside unusually dense mineral concentrates. Magnetite, iron-rich grains, small garnet fragments, and other resistant minerals that survived transport. This does not prove a connection, but it raises an important geological question. Why are these materials occurring together? To answer that question, it helps to understand how rivers sort material. Fast-moving water can carry surprisingly large rocks, but as water slows, heavier particles settle first. That process creates natural concentration zones. Gold prospectors rely on this principle. So do gemstone hunters, and so do field geologists, because rivers often reveal mineral relationships that are difficult to recognize elsewhere. Many beginners assume black sand automatically means something valuable. That is not true. Most black sands are composed of common minerals, but experienced prospectors rarely ignore them, not because the minerals themselves are valuable, rather because they indicate hydraulic conditions capable of concentrating dense materials. In geology, context matters, and context often begins with the unexpected. Eventually, the landscape begins to change. The river channel narrows, bedrock becomes exposed, loose gravel becomes less abundant, and for the first time, we begin seeing rocks in their original geological setting. This is where many investigations become far more interesting, because loose stones can travel, bedrock cannot. Look closely at the network of fractures cutting through the rock. To most people, these cracks appear unimportant. To a geologist, they represent pathways that once allowed fluids to move through the rock. Those fluids transported heat, chemicals, and sometimes minerals. Over millions of years, those processes altered the surrounding rock and left evidence behind. Now observe the color changes. Iron staining, oxidation, weathering products formed as minerals broke down near the surface. These stains are not gemstones. They are not valuable by themselves, but they often reveal where geological processes were active, and that makes them important. Prospectors learn to recognize these subtle signals because they frequently point toward larger geological stories. Dust falls away, a fresh surface appears, and immediately new details become visible. Mineral grains, small structures, subtle textures hidden beneath weathering. This is why professionals rarely judge a rock by its exterior alone. Weathering can disguise important evidence. Fresh exposures often tell a completely different story. See the difference. The weathered surface appeared dull and uniform. The fresh surface reveals complexity. Geology is often like that. The most important information is not always visible at first glance. It has to be uncovered. At this stage, the investigation begins shifting from observation to interpretation. The dark stones are becoming more common. Heavy minerals are increasing. Bedrock characteristics are changing. And multiple clues are starting to point in the same direction. Not toward a conclusion, but toward a hypothesis, a possible source area. Then something unusual appears. Embedded within the weathered rock are fragments that look remarkably similar to the dark stones found downstream. For the first time, the investigation may be approaching their original geological setting. That matters, because understanding a material's origin is often the key to understanding its identity. And if these fragments truly are linked to the Carbonado mystery, their chemistry should match what we find in the host rock. Observe the texture, observe the irregular surface, observe how different it appears from the surrounding rock. Immediately, new questions emerge. Did this fragment form here? Was it introduced later? Is it related to the same geological processes that created the surrounding rock? Or is it evidence of something entirely different? The answer may not be found in the fragment itself. It may be found in the rock surrounding it, because the host rock records the environment in which the material formed. And if the host rock is not what we expect, then neither is the story behind the stone.